Well, good morning and welcome to physics class, second half of this chapter. This is going to be a little heavier than the first half, I think, um, but and we'll see how this goes. I've got the slides, but I'm not sure how long it's going to take me to go through them. There's some terminology, and they're specifically interested in talking about series and parallel circuits. And they give a definition, but they also give some pictures. Let's start with the definition. A series circuit, there's a single path for the current. So if you're looking at letter A there on the left side, you'll see that the current goes through. There's a single loop. It has to go through 1, 2, and 3. It has no choice. The little electron flowing through the wire just goes through 1, 2, and 3. There's only one possibility. In a parallel circuit, there's more than one path for the current to go through. As a little electron's going around, it gets to what they call a node. That's that little black dot that kind of shows you that there's a joint or a junction there. And the electron can either go through 1, 2, or 3. And it's going to depend on how much resistance there is, whether most electrons choose to go through 1 or 2 or 3. That's another story. The main point is that in a parallel circuit, there's more than one path for the current to go through. I'm not sure why they connect this only to series circuits, but they do, and I just went ahead and left it that way. The electrical potential is higher just before a component than just after a component. Any component in a circuit is going to reduce the potential. The electrons have to go through it, and it takes more energy. It takes energy for them to go through it. Now, a wire is not considered a component. We pretend it has no resistance. Obviously, it does. So it's true even of a wire. But of anything other than a wire, it's distinctly true. It's losing energy, okay? And the energy is measured as electric potential. So they talk about electrical potential is higher just before a component than just after a component. Now, the wire is considered to be resistant free, no resistance whatsoever. That's not actually true. There is some resistance. So it's even true of a wire, but of anything other than a wire, it's distinctly true that it takes energy for the electron to go through that component. And because it takes energy, that loss of energy, the fact that it decreases in energy, is measured in electrical potential. And so this decrease in potential is called a voltage drop. So the voltage is going to be higher before a component than after the component, and that's a voltage drop because it's going down. Now, in the context of parallel circuits, this is specifically relevant. A circuit, the current for the circuit is the current of the two parallel paths added together. Okay, remember what current is. Current is how much electricity or electrons are flowing through. If you're splitting it into two parallel paths, obviously whatever you started out with, you're splitting it. Those two split parts are going to add up to the original total, and when it comes out, it's still going to have the same original total. Those electrons can't go anywhere. They're still there. So when they go in, they come out, and some of them go through each path. The number that go through each path added together gives you the total. We often use plumbing as analogies. Your book does it does some with this. If you think of this in context of water instead of electricity, it's not exactly the same, but it gives you a lot of feeling for it. Voltage has to do with how much force there is behind the water, how much pressure, kind of analogous to pressure, how much pressure there is. Current has to do with how much water there is, how much water is flowing. And then resistance has to do with how much friction there is to the water flowing. And so if you think about it, the more pressure you have, the harder that water will go, which means the faster it's going. That's current. But also the more electricity you have, depending on how much electrons there are, and then the resistance will help restrict that because it will make it harder to push the water through. Okay, I didn't do a great job with that. You can check your book if you think that analogy would help you. And I may refer back to it as we go through this. Okay, they do include some symbols here that are useful for you to know. A DC voltage source, we don't use that symbol very often. We use a battery symbol quite often. I stands for current. That little wiggly thing is a resistor. We're going to talk a lot about resistors. But we're not going to talk about capacitors. They're really interesting. They actually kind of like store up electricity inside the circuit. This is one reason why they tell you not to play with like a monitor or a computer. They used to say with the old television screens specifically, which we use for computer monitors. Even if you've unplugged them, they tell you not to play with them if you don't know what you're doing, because there are capacitors inside that stored electricity that could be significant. And then there's a switch to open and close it. Okay, we need to talk about equivalent resistance, because if you have multiple resistors in a system, we need to be able to work with them. Now, in a series resistance, the current is uniform. Remember, all the electrons are going through the circuit. There's no choices. There's no paths. If you're thinking of water, there's like a straight pipe with some sort of a object in the, with the pipe going in and out of that object or component. All the water goes in and all the water comes out. It doesn't matter. It's uniform all the way through. And so the sum of voltage drops across each component equals a total voltage drop across all the series components. In other words, the amount of energy coming into the system, the total drop when the energy comes out of the system, it's doing that by steps through from component to component to component. You add up all the components, and that gives you the total voltage drop across the whole system. They use the illustration in the book, and I didn't draw a picture of this, of a box going down steps. If a box falls down the steps, the distance for the amount of potential energy lost at each step is equal to the total loss going down the entire staircase. So the voltage total equals V1 plus V2, etc. Now the total resistance, if you divide everything by current, then you get resistance on the left side, and you get each voltage divided by current on the right side, which means it's just resistance total equals the resistance is added up. In other words, if you think about it, the resistance of each component is going to be V over I, but the I is the same all the way across. And so the total resistance, if you're dealing with series resistors, you want to know the total resistance of that series, you just add them up. Okay? Those are really easy. Okay, they just said this. Total resistance in a series is the sum of the individual resistances. Just add them together. For parallel resistances, the voltage drop is equal in each branch. Remember, we talked about that a little bit already. So they give the example of a box on the top of a platform, and it's going to go down either a steep slide or a shallow slide, but its drop is the same in both sides. So the total drop is the same. Whether it falls down the steep one or the shallow one, it goes from the top of the platform to the bottom. And they have pictures in your book. I didn't put them in here. However, the sum of the currents in the branches are equal to the current entering the divided circuit. In other words, the total, we talked about this earlier, the total current coming in is divided, so each part adds up to the original circuit. So the total current in a parallel system, the currents add up. The voltage is the same, the currents add up. So we had this equation before, but now see the voltages are all the same because it's the same voltage in every resistor, but the currents are different. And so we can factor this and get this the voltage, which is the same for all of them, divided by all the individuals. And that works us into, we have to, in order to get an answer out of this, we're going to flip this, and then we get 1 over resistance. That one's a little bit not so obvious how the derivation works. But the reason is because the voltage, we now have voltage in the denominator, which is the same, so we can split the fractions out of individual resistors, but it's actually the reciprocals of the resistors. That means that the reciprocal of the total resistance equals the sum of the reciprocals. You can probably already guess this math is not going to be as easy as the math for series. For series, you just add them together. For parallel, you have to do this interesting fraction thing. So because of this reciprocal nature, when you add more resistors in parallel, you actually get less resistance total, which is kind of interesting if you think about it. Okay, but if you add resistors in parallel, you actually lower the resistance total. Okay, so equivalent resistance. Resistance problems can be simplified in steps by using equivalent resistors. And I'm going to give you an example of this. But in other words, if you have a complex system, you can take each section that is either series or parallel and simplify it by replacing it with a resistor that's the same as, equivalent to the others. We had this definition: node is a place where the current divides or converges. Okay. I'm going to give you Kirchhoff's laws. I realize these are kind of redundant. We've already talked about these. A sum of voltage drops in a simple closed path equals the sum of voltage rises in the path. Okay, so in other words, the voltage that you have, the things that you have that raise the voltage, battery, electrical source of some kind, that raises the voltage. All of the voltages around the circuit are going to add, all the voltage drops around the circuit are going to add up to the total original voltage. Okay, so if you have a 6-volt battery, it's going to go down 6 volts worth as you go around the circuit. Okay, as you add each component is going to add up to a total of 6 volts. And we've talked about this one a number of times. The sum of the currents entering a node equals the sum of the currents leaving the node. So how much comes in is how much goes out. So these are algebraic sums. The algebraic sum of the voltage drops and the voltage raises on a path is 0. The algebraic sum of the currents entering and leaving a node is 0. Okay? So, and in order to do this, you have to be careful with your positive and negative signs. And they give you an equation here for potential difference, voltage out minus voltage in, which is fairly obvious. Okay, I think I went through this really quickly, but let me take some time now to do an example problem. Here is a bit of a complex circuit, and I did that on purpose because they have one in the book. On page 457, they have one in the book, and I did mine similar to theirs. And we're going to work through it here together, okay? So here is the full circuit. So we're going to take those 2 resistors at the top of the circuit, the 1 ohm and the 2 ohm resistors at the top. They are series. So since they are series resistors, we can add them together, and 1 plus 2 is 3. So that's the equivalent of a 3 ohm resistor. And you'll notice I have now replaced the 1 and 2 ohm resistors with a 3 ohm resistor. Okay, back here we had a 1 and a 2. Now we have a 3. Okay? Now I'm going to do the one on the left, the parallel circuit on the left. And for a parallel circuit, 1 over R total equals 1 over R1 plus 1 over R2. So 1 over 1 plus 1 over 6. And if you stop and do your math, 1 over 1 would be 6/6 plus 1/6. And so that's 7/6. That's 1 over R. That means R is 6 over 7. Okay, so the total, we have a 1 ohm resistor and a 6 ohm resistor. If you add the reciprocals, you get 7/6. That's the reciprocal of the total resistance, which would then be 6/7. And here we have that 0.857 ohm resistor has replaced the 1 and the 6 have been replaced with a 0.857. Interesting how much lower that is. We start with a 1 and a 6, but the equivalent is less than 1. Okay, because doing parallel resistors lowers the resistance actually. Okay, now we're going to do the 2 4 ohm resistors there on the right, the kind of inner parenthesis kind of. The 2 4 ohm resistors, and they are in parallel. So again, 1 over the total resistance equals 1 over 4 plus 1 over 4. 1/4 plus 1/4, of course, is 1/2. So we take the reciprocals, and the total resistance is 2. So you notice we had 2 4 ohm resistors. Now we have a 2 ohm resistor. Okay, now on that left side of the parallel circuit, we have a 6 ohm and a 2 ohm resistor. And remember, when they're in series, we simply add them together. So we're going to add the 2 and the 6, and that gives us 8. 6 ohms plus 2 ohms is 8 ohms. So we now replace those 2 resistors with a single 8 ohm resistor. Okay, now we have an 8 ohm resistor on the left and an 8 ohm resistor on the right. So we're going 1 over R equals 1/8 plus 1/8. 1/8 plus 1/8 is 1/4. And so the resistance total there is 4 ohms. Okay, so 1 over R total equals 1 over 4, 1/8 plus 1/8. So the total then is 4. Take the reciprocal of both sides. And now we've replaced the two 8 ohm resistors with a 4 ohm resistor. Now we have 4 resistors around the circuit. They are in series, so we can add them together. 3 plus 4 plus 6 plus 0.857 gives us a 13.86 ohm circuit. So we can replace the entire circuit with a single resistor, 13.86 ohms. Remember how complicated that looked when we started? Well, it turns out we can simplify it, and it works out as being a single 13.86 ohm resistor. Oops, sorry, didn't show you the work. There's the work. 3 plus 4 plus 6 plus 0.857 equals 13.86 ohms. Okay, so what's the current in this circuit? Well, we know the voltage and we know the resistance. So from Ohm's law, I equals V over R. You do need to know Ohm's law. V equals IR is very important. So I over equals V over R. So 6 volts divided by 13.86 ohms gives us a current of 0.433 amps. That is the current for the entire circuit, or for the circuit. This is the amount of current going through the circuit. This is how much water is flowing through the pipes, okay? So now we want to look at the voltage across this one resistor. Okay, we want to look at the voltage just across this one resistor. Well, that voltage is going to be the current times the resistance. Now, the current is the current of the system, because there's no branching leading up to this 1 ohm resistor. It's straight through. So the current through this 1 ohm resistor is 0.433. It's a 1 ohm resistor. V equals IR. So we get a 0.433 volt drop across that resistor. Okay? What about this resistor down here, this 6 ohm resistor? Well, again, IR, again, the current is the same because it's just right through the wire. It's a series resistor. The current is 0.433 like it is for the circuit. 6 ohm resistor, that's 2.6 volts. It takes a lot of energy to get through that 6 ohm resistor compared to the 1 ohm resistor. Okay? All right. Now we had this at the point where we had an equivalent circuit here. That resistor is the equivalent of 0.857 ohms. So the voltage across the equivalent resistor, okay, this is treating the two resistors as though they were a single resistor. V equals IR. Current is now the same because what we have here is an equivalent with just one path through it. 0.433 amps times 0.857 ohms gives us a 0.371 volt drop. Not a very large voltage drop there, but that's okay. All right. All right, now we're put it back to where we had it. Now notice the voltage across each resistor is 0.371 volts. This is one of the rules from Kirchhoff, okay? So the voltage drop across the whole thing is 0.371 volts. Therefore, the current drop across each of them is 0.371 volts. It's like that box going down a sharp ramp or a shallow ramp. In this case, we've got the sharp ramp would be the 1 ohm and the shallow ramp would be the 6 ohm. Okay, so the current going through this resistor, I equals V over R. So 3.371 volts divided by 6 ohms gives us a current of 0.0618 amps. Okay. Now we've got that, I wrote that in there, 0.0618 amps through the right-hand resistor. Now the left resistor, the current through this resistor is I equals V over R, again, 0.371 divided by 1 is 0.371 amps. You'll notice that the amperage on the left one is much higher than the right one. That's because the resistance is higher on the right side. So fewer electrons go to the right side because it's harder for them to get through. Some will go that way, but a lot more go through the left one. Okay? So now we have those two amperages marked. And again, left one has a high current because it's low resistance. Right one has low current because it has higher resistance. They both have the same voltage. Now, if we add the current in the two sides, we get 0.371 plus 0.0618 gives us 0.432 amps. There we are. Which is the same as the whole circuit. Well, okay, it's actually 0.433 for the whole circuit. Well, there's a rounding issue. But other than that, so the point is, so the total current in those two branches added together have to add up to the current coming in, which is 0.433. Has to be the current coming out, which is 0.433. And if we add them together, it's 0.432, a rounding issue. Otherwise, it's the same. Okay? Okay, I know that's really heavy. And I apologize for that, but it just is what it is. Give it a shot. We'll be doing homework here coming up, and give it a shot. I'll do another video going over the homework with you. That should be a lot of fun with all these diagrams. But have fun with this. It really can be fun if you get into the spirit of the game. But anyway, good luck with it as we approach the homework. Have a good day, everyone.